So let's start by describing or defining what an inscribed angle is. The inscribed angle. So if you look over here, an inscribed angle is inscribed when the vertex is on the circle.
Inscribed as in like caveman drawings?
Caveman drawings.
Like scribe.
Scribe, yeah. Well, scribe means draw, yeah. To draw or write. And inscribed means that it is created by chords. So notice that this puppy here is a chord. And this puppy here is a chord. So one key feature of an inscribed angle is that the vertex is on the circle. And when I say on the circle, I mean that it is physically on the black part as opposed to being inside, like on the CD, like a disc. Okay. The next part is the intercepted arc. So you could think of the intercepted arc as the arc being eaten by the angle. So vicious angle, eating an arc. So where's that arc? It's this puppy right here. This is the Dorito. Our first theorem to look at says that the measure of the inscribed angle, which is the measure of angle ADB here, is going to be equal to half the intercepted arc, which is this arc here. So arc AB, when you cut that in half, you'll get the measure of the blue inscribed angle there. So let's look at the first example here. Since I have my arc measure right here is 140, all we have to do is divide by 2 to get the measure of the arc inside. Now let's go ahead and show the work as arc measures, etc. So it's a little bit less scratch worky. All right, so the measure of angle X, Y, Z, that's this angle here, is equal to 1/2 the measure of the arc YZ. So what did I do? I said half of the 140 got me to 70 degrees. Taking a gander here, we see that when we take this angle, because it's the inscribed, if we double it, so times by 2, then this arc here is 160 degrees. Now let's see, does that make sense? Well, of course, because if this is a diameter, which it looks like it, notice that we're missing just a little bit right there. Because 180 degrees goes halfway around. So this is just barely shy of 180 degrees. Therefore, 160 makes sense. All right, geometers, let's take a gander at our second theorem here. If two angles intercept the same arc, then the angles are congruent. So let's see what that looks like on the diagram. We have this arc, AB, is being intercepted by 2 arcs, this one here, as well as this one here. Therefore, this angle here and this angle here are congruent. So if I were to label this, the measure of angle ACB is congruent to the measure, actually it should be just simple arc. Let me change that. Just the arcs are congruent to angle ADB. One thing to notice here is that do you notice that there's an A and a B at the beginning and end there? A and a B at the beginning and end there? Because the arc is AB. So the only thing that changes is the vertex.
Wait, what was the question?
Well, if we change our perspective and look rather at, say, this angle here, or this arc here, this arc CD is being intercepted by this angle right here. There. And it's also being intercepted by this angle here. Which means that those two angles there are congruent too. This is congruent to this there. So in the same diagram, depending on which direction you're looking, you have more than one pair of congruents. So it turns out that angle CAD is congruent to angle CBD. And again, make note here that the arc CD shows up in both of those angle names. So let's look at this diagram here. Notice that this angle here is 62 degrees. And it intercepts this arc right here. So let's see, is there another arc, or excuse me, another angle that's intercepted by that arc? WZX also intercepts that, which means this guy here has to be 62 degrees as well. Now, if we turn our perspective around and look at a different angle, or excuse me, a different arc, this arc YZ right here is intercepted by this arc, or this angle, and this angle right there. So we could actually identify two other angles that are congruent there based on the blue arc. So we would say that angle ZWY is congruent to angle ZXY. And again, where are those two? It's these two here and here. Those two there. Inscribed versus circumscribed. So, of course, as we saw earlier, yes, gentlemen, I know what you're thinking about circumscribed. Please think about it and forget about it now. In means inside, scribe means to draw. Circum means to go around, like to circumvent a situation. You would go around it, or as you boys are thinking, whatever you're thinking. Okay, circum goes around to write something around. So take a gander here. If you have a circle and a triangle, I can talk about the same description, or excuse me, the same object here, the same drawing, from two perspectives. It's kind of like this, where I can say, my little brother's name is William, or I can talk about my brother and say, my little brother, William's big brother is Wesley. That would be my name.
Brother really named William?
True story.
My brother's name's Jason.
So, we can, it depends on who you're talking about, that if I'm going older or younger. Same thing here. Whichever shape I'm talking about will determine whether I go inscribed or circumscribed. So, let's look at the first way of talking about it, where we would say this. The circle is circumscribed about the triangle. Okay. Now if we go from the perspective of the triangle, we would say that the triangle is inscribed in the circle. All right, this next theorem says if a right triangle, and that's ugly, a right triangle, and so it's this triangle here, is inscribed in a circle, then the hypotenuse is the diameter. And that is the diameter of the circle. Looking at this diagram, notice, number one, I have a diameter right there. Since this is a diameter, what can you say about the angle T across? This angle exactly is a right angle. So if that's a right angle, then my super secret equation that I can use here to solve would be that 15x equals 90. So simply solve to get x is 6. And the last theorem we'll look at before we give you a few minutes of practice on the next page says this. And I'm going to try to fit it in there, a quadrilateral, so any four-sided polygon, can be inscribed in the circle if and only if its opposite angles are supplementary.
You give a longer line for supplementary and quadrilateral.
Yeah, maybe I was on those painkillers. So let's apply that theorem to this diagram. First off, we know that this is a quadrilateral, of course, because it has four sides, and each of the vertices are on the circle. So now the opposite angles, so in other words, the measure of angle D plus the measure of angle F, those are opposites, they're supplementary. So they add to 180. And I can say the same thing for the other pair of opposite angles. The measure of angle E plus the measure of angle G is also equal to 180. Notice that this angle Z is opposite the angle X. So these are opposite angles here, the angle Z and the angle X, so they are supplementary. So now we can go through and solve accordingly by subtracting 126 from both sides to get your answer. Now when we look at the blue angles, they too are opposite. So now when we set them up, their measures add up together to be 180 degrees. So continue solving this one to get your value of x, which ultimately is 6.